Hello, everyone. Welcome to our Ecosystem Observations TERN webinar, the last of the year. And it's great to see people coming join us from everywhere in the world. It's very nice to see you today. And for those that haven't met me, I'm Beryl Morris and I'm the Director of TERN. So today's webinar we've called Integrated Earth, something that I'm very passionate about. And just move on. The first thing I'd like to do is acknowledge the traditional custodians throughout Australia and all nations. And we love to honour their connections to the land and water and biodiversity and culture, and pay our respects to the elders past, present and emerging. So a little bit about TERN before we get started. TERN is a national research infrastructure project in Australia, which means that we're the group that is monitoring changes to Australia's ecosystems. We have people using our infrastructure from everywhere in the world, and they are using it to monitor and understand changes to our environment, not just Australia's environment, but anywhere in the world that needs Australian data, and climate, so that we can enable predictions of future risk. TERN is not just a single entity, it's actually made up of many partnerships, and funding comes from the Australian government and several of the state governments and many, many institutions. It wouldn't be possible without that very large collaborative effort. So today's webinar, Integrated Earth, Linking Our Planet's Processes from Core to the Atmosphere. This has been a big theme for us in Australia this year. We've been having a look at how complex some of the challenges are to the environment and to society, and really recognising that we need to understand what's happening at all of the sphere levels on the planet in order to be able to make some predictions about the future. So we have pulled together a star cast to talk to us today. We have David Gwyther, who is from the University of Queensland, and David is going to lead off our webinar today. He has the good fortune of cutting across quite a few of those spheres that I just showed on the last diagram. And I first heard him talking about cryosphere, but he is very well organised in atmosphere and so on. I think if people, I do have a raised hand, if people can put their questions into the chat, so that, because we won't be able to stop the webinar. Our second speaker is Sam Provost, who's from the Australian National University, from the Fenner School. Sam's doing a PhD and is focused very much in our biosphere space. And the last speaker is Dr. Rebecca Farrington, who's from a colleague at another one of the interest-funded projects, OzScope. And Rebecca is going to talk to us a lot about the data challenges related to integrating our Earth. And if you want to know more about these people, please go to their bios when you registered. Now I'm going to hand over to David to take us off and start speaking, and he'll then hand over to the other speakers, and I'll see you at the end. Thank you.
Thanks, Beryl. I'll just share my screen. And minimize. All right, so my job today is to convince you that the cryosphere is interesting and useful for terrestrial ecologists and those that are interested in the terrestrial ecology of Australia. A quick recap, if you don't know what the cryosphere is, it's all of the frozen water components of the Earth system. I'm going to focus in more on four kind of aspects of the cryosphere. The first are the ice sheets, the Greenland and the Antarctic ice sheet, but again, I'll focus more on the area that has more kind of research relevance really for Australia, which is Antarctica. Antarctica is about twice the size of Australia, and it's all of that massive ice that's sitting on top of bedrock. In fact, there's so much ice there, if you took all of Antarctica and melted it, collapsed it into the ocean, global mean sea level would go up by about 60 meters. There's a lot of ice there. It's slowly flowing out through these relatively fast flowing glaciers. And then where those glaciers hit the ocean, they begin to float and they form ice shelves. And these ice shelves can be, again, very large and in some cases, many kilometers thick, but they're characterized by having ocean beneath them, this ocean-filled cavity. That's the continental ice. And then the other important component is the sea ice. This is the surface of the ocean that freezes in winter and then melts again in summer. So you've seen these images of it kind of pulsing in and out with the season. That's the recap. I just want to give you a quick summary about what I'm going to talk about today. I'm going to do a quick overview of some interesting Antarctic ecology, and then look at what the impact the cryosphere has on the globe, and then focus in a little bit more on what Antarctica can tell us about Australia. And I should give you a disclaimer that I'm not an ecologist, so if I sound like I'm talking with authority on that, I'm not. So the cryosphere influences the local ecology in Antarctica, obviously. This is an example from a recently published paper. The red line on the left is the sea ice extent that's been measured in the 2022 sea ice season. You would have seen that over the last 2 years, there's been record low sea ice concentration, in fact, or extent, something like 6 to 7 standard deviations below the mean, and the mean is shown here with that orange line. Unfortunately, this kind of weaker sea ice season coincides with when emperor penguins are crashing and then fledging. And if you see this, what this kind of looks like spatially, on this right panel here, they've shown the West Antarctic Peninsula, and then there's sea ice anomaly, over 100% below the mean. The result of that, and this coincides with all these important emperor penguin colonies, these are locations that have been kind of continually used for many years. We are using satellite observations. They identified when these colonies were populated, and that's shown with these yellow circles. But as they looked through the season, they found that they were actually abandoned before the fledging could finish. So all of these colonies failed. In fact, there was this kind of catastrophic breeding failure. And I guess the reason why you care particularly about this is that emperor penguins are unique for a large vertebrate species in Antarctica, because they have not really been subject to widespread hunting from humans. They haven't really been subject to habitat loss, don't have that pressure. It's really only the influence from climate change that's impacting this population. So I guess you could imagine, you could kind of picture it as a canary in the mine species for how population will adjust to just the impact of climate change in a location where we know that in Antarctica that climate change is presenting itself rapidly. I wanted to move on to another aspect of ecology in Antarctica, which is quite interesting. This is below the ice shelves. This is actually, imagine boring a hole through the ice, maybe 500,000 meters down, and then popping into that water-filled cavity beneath it. When they did this and they turned on the lights, this is what they saw. Firstly, this kind of thriving ecosystem of amphipods, small kind of shrimp-like critters, a few centimeters long. And then on this image, this video on the right, same thing. They drilled through, and then they lowered down I think it might be the drill with a camera attached to it, happened to drop it right on top of this boulder, which actually was quite fortuitous. This boulder didn't just appear there. In fact, it's probably like a glacial dropstone. So some thousands of years in the past, it might have been frozen into the bottom of a glacier in an ice shelf, and then it's melted out and dropped into the ocean. And it's provided this perfect environment, it seems, for all these this community of sponges. So these communities aren't just kind of existing for no reason. We know that it's unique because it's between 500 and 1,500 kilometers from the nearest photosynthesis. They're highly dependent on the influx or inflow of nutrients and minerals. And the only way this is arriving is from the cryosphere itself. It's coming from the subglacial hydrology, the water that's melting on the underside of that large ice sheet and squirting out into the ocean and carrying all these nutrients. So these environments are kind of these, I guess, very interesting ecological test beds for a location that's very tightly coupled to the physical system, the cryosphere. Okay, let's move on a bit and look at how the cryosphere contributes more globally, in particular sea level rise, and then try and tie that to how that impacts Australia. You probably would have seen figures like this showing the time series of projections of global mean sea level, which have suggested that by 2100 we're seeing 0.5 meter to a meter roughly of sea level rise globally, and that's dependent on which scenario we follow. But you'll see that firstly they follow they're projecting a straight line, and they're also projecting these large error bounds. What those error bounds are kind of capturing, or not capturing as it were, is that there's a huge amount of uncertainty in how the Antarctic ice sheet is going to react to warming oceans and eventually warming atmosphere. In particular, there's potential for rapid ice sheet collapse. This is a series of satellite images of the Larsen B ice shelf, which completely collapsed in 2002 over the course of a few months. Now, this is fairly small, you know, kind of I think it might be the size of like a small state in the US. But we know that this similar mechanisms could actually occur to large drainage basins, which would directly impact sea level rise and deliver many meters of sea level into the ocean. And they could do this on rapid timescales. And lastly, they're irreversible. We can't just freeze them and put them back up. So understanding that and capturing that in models is a large challenge that we face. And I've said this global mean sea level rise, but we know it's not going to happen globally on average. We know that there's going to be an uneven distribution of that sea level. And that's because when you remove that huge mass of ice, the entire gravitational field of the Earth adjusts. In fact, the rotation of the Earth will need to change, or will change. Such as in the simulation here, where they collapsed the whole West Antarctic ice sheet, something like 3 to 5 meters of global mean sea level rise. They took that, put that into the ocean, and what they found is that, as I just said, the gravitational field adjusts, the rotation adjusts, and you get these hot spots of sea level rise. So these are kind of like, you can imagine as like a sea level fingerprint, fingerprint from a particular glacier or drainage basin on the ice sheet. So you could choose some region of Australia that you're particularly interested in, and using simulations like this actually kind of fingerprint your own kind of doomsday glacier, the one that's got the most connection is going to lead to the biggest sea level rise in your location. The cryosphere is also important for the climate as well as sea level. As I said, sea ice forms around Antarctica before winter. This image on the left demonstrates a location where this is happening very strongly. You can see these streaky bands of fresh ice being formed, and as they're formed, they're blown out of the way. And as it forms, that salt can't be fully captured in the ice matrix, in the sea ice, and so it kind of rains down as this salty brine. This gets denser and denser and forms very dense water, which then sinks off the continental shelf. And this occurs at these 4 locations around Antarctica. As this sinks off Antarctica, it contributes to this global meridional overturning circulation. This is one of these large-scale currents that kind of goes from pole to pole and around the ocean basins. And you can kind of imagine it like a conveyor belt, where Antarctica is the kind of spool that's driving the bottom return of that conveyor belt. We know from observations that the formation of that dense water is beginning to shrink, contract in the amount of volume that's producing. It's getting fresher and so on. So we know that there's the potential for the interruption of this global circulation. Indeed, there was a paper that just came out fairly recently. They used a dynamic system approach. I won't go into this in any detail, but they suggested that we've actually passed a tipping point. It's reached all the criteria of passing a tipping point. And they suggested there's going to be a collapse of the meridional overturning circulation by 2055 with some error. If that did happen, you would expect to see Europe get much colder. You would see the east coast of the US experience different weather through the shifting of the storm patterns. And then perhaps with the greatest impact, the climate across the north of Africa is going to change dramatically. The precipitation will move southwards. And so a band that's called the Sahel, which is south of the Sahara, this is a region where we know there's a very strong link between political stability and precipitation, rainfall patterns. And we know that this would be greatly impacted if this happened, negatively impacted. So whether or not you kind of believe this exact model, I think what is clear is that we need to understand more. I guess this is where I come in. I run high-resolution numerical ocean models of Antarctica, but also the east coast of Australia. And I'm particularly interested in the way the ocean interacts with the cryosphere and the atmosphere, for example, through better trying to understand sea level contribution to sea level rise and dense water formation. So let's zoom in a little bit more and try and understand what the cryosphere can tell us about our own backyard. And this can be done through looking at ice cores. This is where they drill down into the ice and pull out a core of ice, and then very carefully do chemistry on that through down the core. And using the high resolution chemistry at high resolution, you can understand conditions in Antarctica, and through the kind of synoptic links, these kind of weather patterns that are kind of linked between Antarctica and Australia, you can understand climate in Australia. For example, snowfall at Law Dome, which is a location in East Antarctica. This is on this bottom line here. This is showing snowfall there. Correlates very well with rainfall in Western Australia. We can go a step further. You can combine that snowfall accumulation with the concentration of sea salt in the ice. And using what these Tessa Vance and other authors did, they combine that in just two different ways and produce these red and blue lines. This is representing a climate mode called the Interdecadal Pacific Oscillation, or IPO. The IPO is one of these long-term climate modes. So it has a longer term period or periodicity than ENSO, for example. But we do know that it's a strong indicator of whether Australia, Southeast Australia in particular, sees drought or fire weather, or if it sees rainfall and flood weather. And you can see with this black line here, which is the observed IPO, how well that's reconstructed using those red and blue lines, the models. So you can predict this, you can understand IPO directly from measurements of ice in East Antarctica. And then you can use that high resolution data and go back 2,000 years. This black line here is showing again that observed instrumental IPO proxy or metric. And the purple line shows what was measured from the inferred from the ice core. And what this study has shown is that Southeast Australia is actually 3 times more likely to be seeing drought and fire weather than what we've seen since 1877. So actually, since 1877, it's been a much anonymously wetter period as compared to the whole period. And you can kind of see that with these bands here, where this latest period is actually much more blue. The other results from this study suggest that these periods, this negative IPO, which means more flooding, they're actually likely to be shorter, less than a decade, as opposed to the kind of multi-decadal periods of drought which appear in the record. So just to summarize and kind of bring that together, there's 3 things to leave with you. Firstly, the cryosphere is this kind of ecological and ecosystem testbed for understanding these impacts of climate change. It's also a source of influence on the global climate and sea level, including what we see in Australia. And then that is also recorded in high resolution, particular conditions and climate change in Australia. And I'll leave it there. Thank you. And are we going to hand straight over to Sam?
Yep.
I'll hand on to Sam. Thank you.
Thanks, David. Yeah, that was really interesting and quite terrifying. So I'll jump right in. This presentation is called Caring for Landscapes with Integrated Data, Reflections from UBIR. And my name's Sam. I'm a PhD candidate at the Fenner School of Environment and Society at the Australian National University. And the focus on my research is to work toward better landscape management through assisting Indigenous communities to map their cultural values and, where appropriate, integrate these data with existing environmental data. And in this brief presentation, I'll first talk about how the increasing occurrence of natural disasters highlight the need for high-resolution integrated data. And I'll then draw on a First Nation-led project that I've been involved in to discuss the types of data integration that could help humans to better manage biodiversity, landscapes, and country. So in the last 3 years, we've experienced an increase in natural disasters that have showed us that we need accurate, relevant, timely, integrated data for planning for and responding to environmental crises in real time. We need this as disasters occur and afterwards to help the people, biota, and landscapes affected to heal. The 2020 Black Summer fires tore through more than 8 million hectares in southeastern Australia, killing 33 people and 800 million animals in New South Wales alone, and putting many endemic plant species at risk of regenerative failure. 2 years later, we saw the Northern Rivers floods, the largest floods in modern Australian memory and the most expensive disaster in Australian history. These floods and the devastation they wrought proved that the boundaries that we think separate land and water, sea and skies, can be unmade so quickly. In December and January 2020, the Black Summer fires demonstrated that we need to better understand and respond to the relationships between fire dynamics, fuel loads, weather systems, species distribution, biodiversity networks, global atmospheric circulation, such as the movement and impacts of wildfire smoke across the planet, as well as how all of these impact the resilience of infrastructure and communication networks. The aftermath of the fires raised key questions that have dominated research discourse, government funding agendas, and local community-led recovery projects in the last 3 years. Questions like, how do we calculate damage? How have ecosystems and landscapes changed? And are these changes permanent? What are the impacts on surface hydrology and groundwater? How do these impact revegetation? What are the impacts of the fires on the atmosphere and the hydrosphere? What does healing look like? Now, I don't think we can adequately answer any of these questions from within our disciplinary silos. And to be clear, I'm not arguing that specialization isn't important. Of course it is, but the reduction of environmental science into siloed and distinct disciplines has left us without any viable ways of integrating these data streams to make important decisions about the management of the landscapes we work and live within. So how can we begin to grapple with these complexities? This is an issue that scholars working through a lens of Indigenous methodologies have been grappling with for a long time, and there are some lessons to be learned here. I want to briefly step through the need for integrated data models in managing landscapes via a project that I've been involved in for 3 years in Kakadu National Park. The Ubia BIM Conservation Project brings together binning traditional owners, Kakadu National Park staff, geographers from ANU, and archaeologists from the University of Sydney, Flinders Uni, and the University of Notre Dame. The project was originally focused on protecting the cultural heritage of the Ubia Rock Art Complex from an archaeological perspective, which involved identifying and ameliorating negative impacts on the rock art. And this is a photogrammetry model of the Ubia complex captured with a DJI Inspire 2 drone and processed in drone deploy. And you can see the northern aspect of the main gallery and the Nadab lookout. So while the project began with a focus on, you could say, traditional archaeology, through a process of mapping Aboriginal cultural values with the binning traditional owners, we quickly saw that the issues impacting the rock art are the same issues impacting the biodiversity and the ecological dynamics of the region, because all of these systems are linked. They exist in a relational network, and any effort to separate out and deal with them independently would mean ignoring a range of connected factors. So the Ubia project has shown that regardless of what discipline you approach research from, when operating in a cultural landscape, the requirement for integrated data will arise quickly if First Nations people and knowledge systems are engaged meaningfully and not just as a tokenistic gesture. And this is in part because Indigenous ontologies are built around relationality. As an example, let's consider the widespread use of the Aboriginal English word country. One of the most illuminating definitions of the word comes from Bawaka Country et al. 2016, where they write that the word country comprises all humans, more than humans, all that is tangible and non-tangible, and which become together in an active, sentient, mutually caring, multi-directional manner. Now that's a lot, but put another way, country is both fluid and generative. It weaves together the biophysical, sentient, and intangible elements of land, sea, and skyscapes and holds them all together. So from this perspective, we found that the BIM, or the rock art, is being negatively affected because country is changing. This network is shifting. And to understand the complexity of these changes requires a range of multispherical data, including from the geosphere, information about rock composition, weathering, how chemical processes are affecting the art over time, biosphere, species distribution and how they're interacting with the art, pest species, endangered species, fire frequency and severity. We're finding that the ash and the charcoal is adversely impacting the rock art, hydrospheric data, inundation of the region, the salt content of the water, what aquatic species and habitat is there, seasonal changes in water levels and composition, and how these are changing over time with sea level rise. We need atmospheric data, climate change modeling, seasonal dynamics between the dry and wet seasons and how they're changing over time based on the anecdotal evidence that we're hearing, impacts of temperature increase over time. And then there's this layer of the cultural, which is inherently contextual. It's both tangible and intangible. It's multimodal, meaning it's stored and shared in many different ways. It's often holistic, meaning that you can't discuss one object, area, plant, animal, or person without also considering a range of related information and relationships. And then beyond this, we need accurate data on tourism, who's visiting the area. And we need these data at fine scale resolutions. So we're using drones and ground truth spatial data. And we need to feed into remotely sensed data at the landscape scale. And ultimately, We need all of this data to be integrated and accessible through user-friendly platforms that encourage exploration and creative analysis. We need architecture that allows for the safe and culturally appropriate overlay of Indigenous cultural values with Earth systems data. Excuse me. So in general, Indigenous data has historically been a missing layer in the landscape management and environmental science. This is largely due to the exclusion of Indigenous people in decision-making processes, which has led to avoidable harms, such as building towns in areas known to local Aboriginal people as high flood risk areas, or the senseless destruction of millennia-old cultural sites such as Juukan Gorge in 2020. But there has, however, been an exponential increase in reference to Indigenous knowledges and ontologies within the space of environmental science over the last 20 years. And the increased appetite for including Indigenous knowledges in environmental research appears to have largely come from an acknowledgement that Indigenous peoples have adapted to a range of environmental crises over the last 60,000 years, and that those experiences could help to address the climate issues humans face today. Now, if you want to learn more about this and the ways that environmental research alongside Indigenous peoples can be built around the principles of Indigenous data sovereignty, then you can check out a paper that my colleagues Bayami Williamson and Cassandra Price and I published in Environment and Planning. The paper is called Operationalizing Indigenous Data Sovereignty in Environmental Research and Governance. And I would also suggest heading over to the Mayamnari Wingara website to look at the recent Indigenous Data Governance Communique, which was agreed to by more than 150 Indigenous people at a symposium in Cairns earlier this year. Now to sum up, I use the example of the BIM conservation project because I hope that it might urge us to think about how, what our capacity to integrate and represent data in meaningful, respectful, and inspiring ways might be, and to tell the stories about our landscapes, seascapes, and skies that we all need to collectively listen to, so that we may find ways of re-engaging the planet to serve and protect life across the entire Earth system. So I'll now hand over to Rebecca, and thank you.
Thank you, Sam. That was wonderful. It's always great to get so many different perspectives in the one seminar. Okay, hi everyone. So yeah, Beryl asked me to come and present about integrated Earth from a data perspective. And my name's Rebecca Farrington, and I'm the Director of Research Data Systems at AuScope. AuScope is Australia's geoscience research infrastructure provider. So we're the cousin of TERN. And we provide field instruments, laboratory equipment, and access to compute and storage for geoscientists. We also fund the people that are required to run the equipment and to go on field deployments, as well as software developers to develop code to model and simulate the solid Earth system. So we kind of look at the solid Earth surface and below. And I suppose my job is to make sure that the data that is created by all of these instruments and people is stored appropriately. So it's still aspirational, but all of our data is supposed to be stored under and curated under the fair and care principles. And that requires, I suppose, a lot of community development and work, as well as making sure that our researchers have storage to actually put their data. We operate in things like groundwater, as well as hazards with earthquakes, etc. We've got telescopes for global positioning and geochemical equipment in laboratories, trying to understand the age of rocks and what the rocks are composed of. So lots of different types of data sets that we have. And as a general philosophy, we provide there are different communities with different data resources. So some communities have very data intensive needs. So, tens of terabytes of modeling output for large scale Earth simulations. And then on the other side of the scale, very small data output from geochronology, which is trying to understand the age of rocks using various geochemical analysis techniques, where what we often say is an entire researcher's work can be held on one small USB stick. So we have a very broad community. And in the integrated Earth context, if we extend that out past geosciences and into all of the different spheres, that only kind of multiplies in terms of scale of volume and use cases. So we do collaborate with people all across Australia. So that again feeds into the diversity of data sets and data needs. This is a figure that we've only recently been exposed to last month at the National eResearch Conference that was up in Brisbane. And I felt it was a really great figure to share today, because it does talk about the different types of data and trying to understand what type of research problem people are trying to address. So in terms of the National Research Infrastructure Facilities for Earth and Environment, it's highly variable, lots of different impacts, lots of different use cases, volumes across multiple scales, as well as costs. And that is then multiplied across the data collection phases, the data analysis, data delivery, data curation, and data retention. I'll just work through this slide because I think it's quite interesting from my perspective. So I apologize if it's fairly boring for others. It's looking at the type of resource that's needed versus the impact, and we can see it kind of hits on fundamental research, applied research, decision making, and into operational. And you can see that depending on where we sit, it really does depend on then how much it costs. And that cost can be in dollar terms, but also in terms of impact, and also in terms of volume that's needed, so for compute or data storage. And so what's interesting is we talk a lot about decision making. Okay, so in terms of impact, right? So we do a lot of research in Australia, but making sure that that can be put into decision making and policy, but then also being pushed out operationally is where impact can be seen. But a lot of that is kind of down the pipeline there in fundamental research and applied research. And Earth and environmental data, and specifically to integrate that, we need to look across all of these different scales. In the context of AusScope, I just wanted to touch on just 2 use cases of projects that we have that I feel are relevant to this question of how can we integrate Earth's data sources in the Australian context. And we've had a project that's recently completed, and we're holding a workshop this month up in Canberra. It's called the 2030 Geophysics Collection Project, and it was a research and development project. We collaborated with NCI, the National Computational Infrastructure, which is a supercomputing facility in Canberra, TERN, and the Australian Research Data Commons. And it basically came out of having a large magnetotellurics campaign across Australia. So that was co-funded by Geoscience Australia, AusScope, University of Adelaide, and various state geological surveys. And those dot points in the Australian map show where they had field equipment for certain periods of time. And this data can then be used to produce a continental scale electrical sensitivity map, which is of use in lots of different areas, from understanding groundwater, space weather impacts, to mineral exploration. But the problem was that data hadn't been curated. So there had been research outputs from that data, but to understand the importance of, I suppose, the lifetime impact of that data set hadn't been realized. And so we went about it turned into a data rescue operation, but we rescued the data from various researchers and consultants. But what I think is important in terms of integrating that data with other fields is that we really had to look closely at the processing levels. So in that bottom table there, on any instrument, you get different types of data, and what is actually produced as the research output is quite different. So it goes through different levels of processing. So that can be, you know, the analysis phases that is the nuts and bolts of people's scientific discipline. And in this case of Geophysics 2030, we were able to rescue from raw data and then also provide the data at different processing levels. So independent of what stage of data that you're interested in, you're able to access that now. So if you're interested in the research output, so you know the maps of electrical sensitivity across Australia, you can access that. But if you wanted to get the raw data from different locations, you can access that and then process that in a new or different way. And I think that's really important in terms of integrating Earth's data, because different research disciplines operate at different levels in terms of their core skills. I'm just checking the time. I'll be quick, Beryl. Another really, I feel is an important project that we've been involved with in our global community is CODATA, which is the International Science Council's Committee on Data World Fair project. So we've been very lucky to be able to be involved in this first stage of the project in a group called One Geochemistry. So that's a group of chemists from across the world. There's the Australian geochemists are represented, there's US geochemists and multiple European based geochemists. And when I say geochemists, I really mean the people that are operating the data repositories and the data portals, and some geochemists. And so that's a EU funded project. This petal diagram, if you can see that geochemistry is only one of the petals. Okay, so this is a group of 11 case studies. Yep.
Rebecca, I don't think you've moved your slides on for some time, and we've only been seeing the Ozscope picture, and it's also only in non-full screen view.
Oh my goodness. Okay, can you see the screen now?
Yep.
You've just seen from that?
Yeah, go to full screen mode. And
yep, that's where I was.
I think you might have a different compute. Can you go to reading? Go to reading mode.
Where's reading mode, Beryl?
Right next to the other one, a little book next to the icon that looks like a screen. On the bottom of your.
Are you in slides or PowerPoint? You're in slides?
Oh, PowerPoint.
Yeah, sorry, I'm in Google Slides. I'll just leave it like this if my slides are pretty big. Okay, well, sorry that you missed all that. This is the great figure I was talking about previously. The slides could be made available. There's my map. This is the petal diagram I was just talking about. Thanks, Beryl. Geochemistry is just one petal. And so the purpose of this project is for globally different disciplines to not only do a deep dive into making sure that their data is fair in terms of machine interoperability, and findable, accessible, interoperable, and reusable, but also to make sure that the different disciplines can interact. And so there's been quite a big body of work on what we're calling fair implementation profiles. And so that's to make sure that the data that is made fair is able, if individual communities can articulate what types of resources they've used to make that data fair. And then from that case, we can map between the different data sets. And so to be able to, I suppose, realize a fully integrated Earth data system, these crosswalks between different research domains and different research communities can be achieved through documentation of the fair implementation profiles. I might wrap up there, Beryl, given the time, and I'm happy to take any questions.
That's perfect. Thanks very much, Rebecca and Sam and David. You could all turn your screens on now, because we do have some questions that have come through to me. If anyone's got questions, put them in the Q&A and we will look at those. But the first question I've received is one that says that people are all immersed in their own little area of science because that's how they've traditionally been brought up. How can they keep up with it, with this concept, the growing emergence of integrating across domains? Do we need, the person says, how can we support a community of practice in this area? Do we need a journal? All those sorts of things. So this one sounds like one for the panel, because you're all in this field, and how are you keeping up with it, if you are, and not just in your own little domain? Because we're talking big about integrating, but let's get started and maybe suggestions of how TERN and Oscope and so on can support such integration of thinking.
Does Sam or David wanted to comment? I'm happy to talk, but me? Okay, so I suppose I'm in the lucky position that I'm no longer an academic, a research academic. So I'm no longer specifically concerned with the deep expertise that you, I suppose, are encouraged to develop as a researcher. And my role is to have a look across lots of different things. We've been involved in some key projects that have really exposed where the future is going. And so that World Fair project has been really exceptional for us, and also for that broad community. So those 11 other case studies, getting together so I haven't been going, I have virtual meetings, but we send a representative from that group to meetings to discuss details about cross-domain interoperability, and they go through that full stack of problems. So they can spend a day talking about technical details, and then they have to step back and try to understand how they can step across. How do we get social science surveys interoperable with geochemistry data? And so tapping into those global networks is really important. And I suppose on that World Fair, if anyone's interested or they want to keep an ear out for it, they are planning on expanding it. So it was originally a 2-year project coming to an end mid next year, but they're expanding it. So a lot of the international science unions have become quite interested in that, as well as lots of different disciplines, which is really exciting. So it's almost as if this first 2 years has been a small pilot. But that's not from the researcher context. So it's a bit easier for me to look across things because that's my core skill, but then also that's my role, whereas it's very different for Sam and David, I think.
Thank you. David, do you have any comments? How to keep it all together for everyone?
It is very difficult as a researcher, I think, given that you're trying to write papers, impactful papers, important papers, which often means now that you're diving deeper and deeper. So I don't actually have a magic bullet solution for how to do that. I think especially as a postdoc, younger, like earlier mid-career researcher, it's particularly difficult because you're trying to find job security at the same time. So yeah, I don't actually have an answer for that, other than I think it can't just, it's got to be led better, kind of cross disciplines interaction. We all need to do it, but it can't just be being led from the bottom. I think it needs to be top down as well.
Okay, thank you. Sam, I'm not going to ask you the same question because there's a question for you that's along the line, but very specifically, and you've got a lot of good comments that are coming into you from the chat that I hope you've been looking at. The question here for you is that it's really, really great to see us thinking about Indigenous knowledge perspectives, because it's so complex, pulling together an integrated viewpoint that obviously Western science isn't the total, isn't going to do it. We're going to have to look at different things. How do you think other countries that have an Indigenous community are looking at it? Do you feel that they're connecting into this integrated earth concept and different knowledge systems as well?
Thanks, Beryl. Yeah, I mean, from my experience, and part of this comes from being a executive member on the Mayam-Nari Wingara Aboriginal and Torres Strait Islander Indigenous Data Sovereignty Collective. That is a mouthful. Recently, I've got to spend a bit of time with academics from around the world, sort of talking through a lot of the stuff in Indigenous data sovereignty, and it feels like we're having the same issues everywhere. Doesn't seem like there's one country we could point to that is absolutely nailing it, other than maybe Aotearoa, New Zealand, are ahead of the game across the board when it comes to actually listening to, considering and acting on Maori science and Maori data sovereignty. There seems to be a far better relationship there, and potentially it's because of the Treaty of Waitangi and the history there. But who knows? That's the place where it's happening the best, I think. Otherwise, there's been a lot of work coming out of Canada from Indigenous scholars like Carl Powys White, who's done a lot of work in sort of the philosophy adjacent to this, and similar sort of critiques of that Indigenous people have largely been excluded for a long time, and now the issue is that the inclusion seems like Indigenous people are only being included in these conversations because they might now have something that can help us kind of save us from ourselves, I suppose, rather than engaging meaningfully from first steps. So yeah, I would look to Aotearoa, and then also look to Canada and what's happening in Australia as well.
Perfect. Okay, I've got a big one that's come in here, and that is that the field of Earth observation, taking images from satellites and using them, somebody believes that would seem to be the best way of getting an integrated Earth approach. David, you pointed out a whole lot of very specific examples of events that are happening at a local scale. How would you see us being able to harness Earth observation as an integrator across all nations, and also across all events that are happening, with the ability to know, understand those deeper processes that occur when ice sheets calve and things like that?
Yeah, that's a big question. I mean, I guess the thing with cryospheric science is that, particularly Antarctic science, is that a lot of it has to be remote sensed because it's too expensive to get there, too dangerous to get there, or you can't get there at the right time of the year. All these kind of logistical challenges mean that it's almost, now it's moving to, I think, it's moving to this phase where the kind of remote sensing aspect and the modeling aspect is leading, and then the observational, whether that's glaciological observations or ecological or oceanography, is almost following. I'm sure maybe there's people in this talk, but there'd be probably a lot of colleagues that aren't here that would not agree with that, maybe the observational colleagues. But my sense is that as new technology is being put up, it's pretty rapidly being taken up in cryospheric science. I don't have any sense about how that's how that kind of similar paradigm is occurring, like in ecology and even in land sensing in Australia, for example. I would point out that it's not exactly terrestrial ecology, but there's this new surface ocean topography mission that's just gone up, and that's the idea is that's going to revolutionize the understanding of ocean currents around the globe. So, and that's a similar like the similar satellite will be useful across other methods as well, other geospheres or spheres, I should say. So I think the technology will lead, is my answer, and I think that it's just up to the researchers to try and get on board as quickly as possible and not just get stuck with the old paradigms.
Yeah,
Actually leads into the other thing that I was thinking, which was that final thought about this is that if you look back, say, several hundred years ago, there was this idea of polymaths, which were amazing across a wide variety of areas, and we don't really have those people anymore. So since we don't have that, we need to have some way to kind of emulate that idea of knowledge across spheres, especially given that all of the geosphere and the atmosphere, the biosphere and the cryosphere and so on are intrinsically linked. So it's we either get on board or we are going to miss these important links as we've seen in these talks today.
And Rebecca, in 30 seconds or less, the last question, does Australia need and I'm not sure if this is correct, an exabyte computer capacity to handle such complex things? Is that the size computer?
Yeah, they're talking about exascale now. And so that's not necessarily driven by Earth and environment research. So there is some areas of our research that's pushing the boundary, mainly climate research. But yeah, if we want to be working collaboratively and we want to be, I suppose one of the roles, I suppose, for Beryl and myself as research infrastructure providers is to make sure that Australian researchers have access to the infrastructure they need to be world leading. So we've got great ideas in Australia and we have great scientists, and our job is to make sure that they have what they need. So yeah, we do need exascale.
Perfect. Okay, well, I'm not take any more questions. I'm just going to thank you all. That was fabulous. And for those that didn't notice, there were a lot of links going in to the chat, so visit those before you peel off. It's been great having such a broad audience too from around the world, and I should have mentioned that I'm actually in Korea today, so I've added to the international groupings out there. This is our final webinar for the year. We have some new webinars coming up for 2024, and we'll put those on our webpage. I just wanted to remind you that they're all there. And to thank you for being a fabulous audience, and thank you speakers for the time and effort you've put into integrating all your thoughts for our benefit. So thank you. See you next year.